I'm Mark Adams. Thank you to the Paramount Club for inviting me. This is a swanky place. I feel a little FOMO or whatever, not being able to come here. When I was here, I worked at Leerink, which is upstairs in the building, and if they had this, they kept it a secret from me. Did they used to invite you down here and they didn't let me? The talk is really about artificial intelligence. As you'll see, it's really intended to be a pretty high-level overview. I'm going to get some things wrong, sometimes intentionally, to make it a little easier to understand. Sometimes I just get things wrong. It's okay. It's a big and complicated topic. So just quickly, I have a PhD in molecular biology. My undergraduate was in computer science. Actually, I was doing undergraduate research in artificial intelligence, and I'd like to tell my kids this was in the early 80s when computers were made of rocks, like Fred Flintstone. It's interesting how much of what we use today in form and function is identical to what we were originally doing work on in neural networks, in artificial intelligence expert systems, and so on. It's just what's changed is the volume and the capabilities that have been introduced by the technical capabilities, and we'll talk about that. I have had a varied career. I started doing startup in Cambridge, Massachusetts, biotech companies, largely on the computational biology side. I sort of self-identify as a computational biologist. I've worked in finance at Leerink. I ran an AI group at Bridgewater Associates, a large hedge fund. I've been in and out of biotech, and my last job was Chief Technical Officer and Chief Operating Officer at Adaptive Biotechnologies, which is a publicly traded mid-sized biotech company focused on applying artificial intelligence to analyze sequence data to understand the human immune system. We had a couple of FDA-approved products, which is very unusual, by the way, and Puneet knows this well. Getting a product through the FDA that includes an artificial intelligence component has literally gotten harder. I think it was easier 10 years ago when we did it than it is now. But it's also sort of interesting, and we'll talk a bit about that at the end of the talk as well. Interestingly, both of my kids are now out of college and out of grad school and doing their own thing. Interestingly, both of them are working on artificial intelligence. Apple doesn't fall far from the tree, I guess. My wife's a technical person herself, but retired as a CFO. I'm working as a venture capitalist at Two Bear Capital, which has been very interesting, and it's fun to be on this side of the checkbook for a change, where I get to sort of give the money out. But as you'll hear about, I've been in and out of AI kind of for a long time, and it runs hot and cold. And we'll talk about this. And that's sort of one of the interesting things about the field. But to contextualize this a little bit, this is how strange the world is. This is a legal document. These are the funding documents for OpenAI. This is what's in there. And it says, literally, we're not sure what role money will play in a post-AGI world. Their stated goal, it's artificial general intelligence, and we'll talk about that. The fact that this is a legal document that people are using to make investments today shows you what the weird place we're in very suddenly, right? Do I think that that's sensible? I really don't know, but the fact that it's sensible enough to get by the lawyers in a funding document is strange. So what are the objective today? Let's understand AI's evolution. One of the real purposes today is understanding where AI came from. It did not suddenly appear. It didn't spring from nowhere. It's evolved, and over a pretty long period of time. And now, let's define long. This particular revolution has been taking place roughly over my lifespan. So I was born in 1967, and that's ish and around when this really started to be studied seriously, the 50s and 60s. That's pretty fast as industrial revolutions go. It's incredibly fast if you consider the shift from the Stone Age to the Bronze Age and to the Iron Age. These things are getting faster and faster. If you study Kurzweil, they're doing this, and we'll talk about that a bit also. But I want you to get a context of what's going on, and also kind of just a general idea of what these capabilities are and how they work. I promise no math, not too much math. It's very mathy, but I'd like everybody to walk out of here with an intuitive idea of kind of know how these things work. And I know what people are talking about when they talk about machine learning. What do they mean, really? And then kind of we'll use to provide context as how this is impacting society and what we're actually doing with it. So here's the funny thing. People have been thinking about this for a really long time. You can read the Greeks, you can read Roman poetry about intelligent machines, believe it or not. People have had this idea that you could construct things, the idea of the golem, right? You could go make a thing that can behave like a human being. This is my personal favorite. I don't know if many of you have probably seen this before, the Mechanical Turk. It was nominally a chess-playing automaton, Like you could play chess and it would play you and it would beat you. And you'd open it up and it had all these complicated boxes. Of course, it was a complete fraud. The fact that this open part was for either a child or a small person to sit inside and manipulate the thing like a puppet and play chess, right? But people were all fooled by it. In fact, this has been bought and sold many, many, many times. And in fact, Amazon, AWS, has a tool called Amazon Mechanical Turk, which basically sort of outsources problems to a big network of people who will willing to get paid pennies for the thing that they do, in the idea that, hey, these are problems that only human beings can solve. You would outsource them that way. Let's think of it as an API, an application programming interface, to people. The thing that's funny is that's now defunct. Pretty much anything you would likely do with Mechanical Turk is now being done by an actual automation, by actual artificial intelligence. I find this a hilarious context. Like, here they made this fake machine to play fake chess. Well, the real machines play real chess better than people now, like way better. No human being will be close anymore. Amazon Mechanical Turk, as a joke, but hey, it worked and people used it for that, is no longer used for that. Within, like, this is just a decade, machines have taken over. Interesting. There are also warnings. This is all over science fiction, The Terminator, Skynet. I used Dune. They had a commandment. They shall not create a machine in the likeness of a human mind. There'd been a war and the robots tried to take over and they had to fight them. And they're like, okay, we're not doing that again. Everywhere you look, The Matrix, any modern science fiction movie in some way has a warning about artificial intelligence. It is not like people aren't thinking about this. There's something interesting though, and a lot of our paradigm of what artificial intelligence, particularly artificial general intelligence or AGI, and we'll talk about it, it's very ominous. Is that ominous? Like, perhaps it's good that we're all like, let's not make Skynet by accident, fellas. But it's a little overwrought. We'll talk about why that is. Machines can do a lot more and a lot less than people think, and probably true in at least the near term. The problem is that the long term is getting a lot closer. So provide a little context about where this all came from, and just to give an illustration of what I mean when I say this is sort of roughly my lifetime. The early conceptual foundations, Alan Turing, like one of the real founders of computer science, the way we think of it, and now there are movies about him and everything, which is pretty interesting. But he was already thinking about machines and thinking, how would you know? And one of the things that we talk about is the Turing test, right? Alan Turing's Turing test was a way to tell if a computer was intelligent. You have to realize, machines Alan Turing was programming, you programmed by wiring them up with like a soldering iron, right? These were not programs you sat down and typed programs. But he already was thinking about, whoa, wait a minute. This machine that is made out of relays and soldered wire and whatever could potentially be intelligent. And how would we know? The Turing test was it's sort of debunked now, but the Turing test, he simply said, hey, look, if a computer can have a conversation with people and those people relatively frequently don't know that it's a computer, it's passed the Turing test. Doesn't need to do it always. It just needs to be, it's hard to tell. There was back in the early 2000s, they do this contest every year. They finally got to the point where they were fooling about a third of the judges. Now, it cheated a little bit because it pretended it was kind of a smart-ass 10-year-old. But hey, you got a computer that can pretend it's a smart-ass 10-year-old and roughly get away with it. That's sort of impressive. That test is no longer thought to be a good measure of artificial general intelligence. Partly, you can have long conversations with GPT-4 now, and if you didn't know it was a robot you were interacting with, you wouldn't know. It quite reasonably answers your questions. It quite reasonably gets confused when you ask it silly things. Think of it as your kind of straight roommate friend who gets confused when you try to tease them. So on one hand, you're like, hey, we passed the Turing test. We probably passed the Turing test in like 2010. But really, we don't think it matters much anymore, and I'll talk about that. But the point here is that like people were really thinking about this stuff, and not just things like, can a computer talk to you? Can it solve equations? Can it play chess? There have always been these historical grand challenges that were just thought to be, can it translate language? Now, what's funny is I'm sitting in here with you guys in 2024. Every one of those things I just gave it, can it understand speech? Yeah, probably. Can it play chess? Yep, better than humans. Can it play Go? A much harder game. Yeah, better than humans. On and on and on. Many of the things, can it solve equations? Probably better than people, with very few exceptions. Almost all of the things that they were looking at in the 50s and 60s probably have been solved, not always by artificial intelligence, but people just gotten better at programming computers. right? ELIZA, for those of you who've kind of been around a bit, if you've ever played with the computer program ELIZA or the Doctor, it was a computer program that pretends it's a Rutgerian psychologist, and you literally interact with it, and it would say, well, why do you say that? What makes you feel that? It would repeat back. What makes you say blank? It wasn't convincing, I mean, but it was a little eerie to like be typing on your terminal with this thing that would ask you kind of psychologist-like questions. And the interest was like, hey, how close is this to interacting with a person? And that program was very simple, maybe a few hundred lines of Fortran. But what happened in the 60s, though, right, is people started to get pretty excited about this, the perceptron, artificial neural networks. We'll talk about these things. And it ran the hype up. It ran the hype right up into the first AI winter, right? Like in the late 60s, people were trying to build machine vision. This was the thing that drove it. Largely, interestingly, being driven by the Vietnam War, right? They wanted machines that could do a better job for missiles, whatever. And it just, the machine vision stuff that you could build in the late 60s just wasn't up to it. The computers were too big, they were too heavy, it wouldn't work. This led to the first, no, we're not funding anything labeled AI. When I was an undergraduate in the mid to late 80s, we struggled a bit to get research funding because people were like, no, AI, bogus, whatever. By the end of that point, by the late 80s, people were like, AI, that's super exciting. It was starting to be applied to actual tools. And in fact, handwriting recognition. The handwriting recognition in the Palm Pilot is an early application of that kind of machine learning technology. But again, they called that the AI summer. I was lucky to be sort of doing research during the AI summer. By the time I was in graduate school in molecular biology, I was told to take AI off my CV because you were not serious people if you were a circus clown. Take it off. And that circus clown lasted, by the way, all the way through a lot of this, right? Despite the fact that Deep Blue won chess, Jeopardy won, Watson won Jeopardy. A whole bunch of things happened during this time, but it was still really, people stayed away from the term artificial intelligence literally because the AI winter was sort of thawing out, right? What really caused the last iceberg to go plop was the invention of deep learning by Jan LeCun, right? And we'll talk about what deep learning is, but it was a spectacularly powerful technique. And suddenly people whoa, maybe this is back. That got me my job at Bridgewater, when suddenly forward-thinking people, still rather forward-thinking, AI wasn't a big deal yet, but it was starting to be a big deal. And people who had the resources were like, yeah, we want that, and started to invest in it heavily. And of course, when people invest in things heavily, they come back. It was interesting that suddenly people wanted the AI back on their CV. Oh, didn't you do AI, Mark? You should put it back on your CV. Okay, it didn't change anything. But I worked, and the guy, the guy who built Watson for IBM came to work for us at Bridgewater, and a guy named Dave Ferrucci. And one of the fascinating things was the complexity of Watson. We tend to think now, it's been so long, it's been 10 years. We tend to think of these sort of GPT-type systems as almost programming themselves. They're relatively prompt-driven. Watson was a construct of literally dozens of different algorithms and a very sophisticated voting technique to figure out what was right for each problem. It was a very Rube Goldberg-y thing. It worked real well. Kind of worked like people, right? I got all these heuristics and I'm just good at figuring out which one to use. But it wasn't. It was one of these things where you open the box and you're like, yay, that's complicated. Close the box. Again, just as a piece of history, it is not surprising that what I'll call Dr. Watson, that's the application of Watson, the technology they built to win the game show, utterly failed in medicine. Utterly failed in medicine. MD Anderson invested $100 million in that project along with IBM, and it just blew the tires out. Now you might say, well, Mark, why is that? Think of it this way. If you decided you had a new way to teach people medicine in medical school, and you said, my technique is I'm going to get people who are really good at Jeopardy, and I'm going to give them a stack of medical textbooks and send them home, and when they get back, they can start diagnosing patients. You wouldn't think that would work, right? It's a different skill set. Not surprisingly, it didn't work, right? But look, the beauty of it, and I think one of the really neat things I'll say this positively, about the latest thaw in the AI winter is that didn't kill it. By all rights, that failure, just absolute failure of Watson in medicine, should have literally just like brought this thing to a halt, and we're right back to AI winter where we all like to be. But they didn't. The reason they didn't, and kind of past this diagram, we'll talk about the new stuff, is there's been new thing after new thing after new thing that are showing real progress. And I feel like the ball's rolling downhill. I think, yeah, it's still, if I were making a bet, I'd say it's probably still going to be an AI winter because that's just what we do. But it's fascinating to watch this up and down, up and down, up and down, up and down. And suddenly, over the last, like literally, like 15 years, it's been up and up and up and up. So, you know, and again, I won't belabor this, but it's like overhyped expectations. Is this sounding familiar? Overhyped expectations, people running out of money. What isn't going on here is limited technological abilities. You know why that stuff we were doing when I was an undergraduate, which is basically neural networks and, you know, expert systems and all the same kind of tools and techniques, why did those sort of not do anything particularly interesting beyond, let's say, handwriting recognition? We didn't have enough data, we didn't have enough compute, we didn't have enough memory. We are in a position right now where we have functionally, for all intents and purposes, infinite compute, infinite memory, and roughly all the data available to the human species, period. This is why these large language models work. My younger daughter works at Adept AI in San Francisco. They're building a foundation model. They took $500 million last year in investment. What are they going to spend that on? Not chairs, I mean only like 50 of them. They're spending it on compute. The fact that they can get that compute is utterly transformational. Believe me, like when I was doing it, we had a box, and the box was under your desk and generated a sizable amount of heat, and you had floppy disks to put in it. I mean, you just can't do that much. So where would you get the data? The internet, cloud computing, and vast improvements in storage technology means that all of a sudden, one of the real things that has blown this out is people just ran into the limitations technologically, and that just isn't really a limit right now. It's money. As long as you can get funding, you can do it. So let's do a brief tour. Like, let's talk about what are these AI approaches? Like, AI is a whole bunch of things. This is one of the things that really, this is why I say it's easy to get too pedantic. You want to have a ton of fun at a cocktail party? Well, I'm not sure a cocktail party full of AI people is fun, but if you want to try and have fun at that cocktail party, encourage them to discuss what the meaning of AI is, what's in and what's out. It'll probably turn into a fist fight. But, so it's easy to get pedantic. When I talk about artificial intelligence, I'm really talking about a very big market basket of technologies and approaches which are used to solve problems. Like machine learning, you know, expert systems, deep learning, AGI-driven techniques like LLMs, the large language models. We'll talk about these. I'm a big tent AI guy. It's like AI, you know, we'll talk about it. But I'm going to stay very general, right? The idea here is just like, hey, you should get a kind of instinctive idea of what these tools and techniques are, how you might use them, what makes sense and what's ridiculous. Part of the problem is people trying to sell you AI, like just make up shit as far as I can tell. Like literally, it's very easy to just say, AI, it's really cool, it's magic, it'll solve all your problems. It's a set of tools that are fairly well understood. Some things they do spectacularly well, some things are utter failure. If you walk out of here with just a general understanding of the language and an intuition of what might work and when it might not, I will consider it a success. I guarantee you, and I mentioned to somebody earlier, like if in the questions and answers, there are probably people in this room who know more than I do about some of these things, I'm perfectly happy to well actually, it's this and this. There's probably like 100 well actuallys in here. Artificial intelligence real origins, and this is kind of on the left-hand side of that timeline we looked at, were really more around the study of the human mind. People weren't, believe it or not, I tell people this and people don't believe me, we're not really generally trying to make the computer able to do things. They weren't like, oh, we're going to use AI to go solve real world or business problems. That was not what it was meant for originally. It was meant to say, hey, can we understand how the human mind works? How does cognition work? And can we build things that'll be like that? And by this I really mean physical machines. Marvin Minsky at MIT, who taught the first postgraduate AI class I took, was concerned with building an electronic representation of human neurons. He called it the perceptron. He literally wired it together. He made a turtle that would drive around with this 2 neurons, and it was really not a turtle, it was a slug, because like a slug has like some small countable number of neurons. But it behaved in a surprisingly human way, human animal way, like a bug. But that was the thing. And frankly, the researchers were as happy to be surprised by the outcome as they were to solve the problem. Frankly, this is in some sense has driven why we ended up in AI winners and why things were a problem. Because the researchers who were originally doing this stuff weren't really aimed at solving problems. They were aimed at figuring things out. It happens that some really spectacular problems were solved. Equation solvers, winning chess and ultimately Go. Winning at Jeopardy, how crazy is that, right? And it's just a catch-all phrase. I love this quote, right? Which is, the question of whether a computer can think is no more interesting than the question of whether a submarine can swim. It's going to do human-like things in an utterly human-unlike way. It's funny, this is when I was sort of doing my original AI research. This is becoming less true. And we'll talk about that when we talk about large language models and why they work. So look, like I said, AI is not magic. It's just applied mathematics with a lot of data and compute applied. That's it. We're going to walk through some examples. And again, these are just things that you'll hear when people use examples, right? Like supervised and unsupervised machine learning. Machine learning is generally in one of those 2 classes. We'll talk about neural networks and kind of an application to that called deep learning. Deep learning is ultimately what won chess. Like Deep Blue is a deep learning approach. Adversarial techniques and stable diffusion. Adversarial techniques because I just think they're really interesting and the fact they work is just shocking. Stable diffusion because where do all those pictures of cats come from on the internet? It just answers a question that I think is interesting. Transformers and large language models. I will warn you, this is relatively easy to understand. These get really hard to understand the details, like really hard. But boy, the things they're doing is interesting, so we're going to talk about it. So first stop, supervised and unsupervised machine learning, right? Machine learning broadly is you take a set of data and you want the computer to label it or classify it. What's this and what's that? That data could be anything. And I'm a life sciences guy. I got a bunch of data from cancer patients and I want to know what stage their cancer's at. That's a classification problem, right? There are 2 ways to do this, right? There's supervised machine learning, right? This is where you start with labels. Cancer, not cancer, and you have some variables. This is 2 variables for 2 dimensions, but they can be n-dimensional. In fact, the more dimensions you got, the better it goes, right? And you're like, okay, I have these labels and I'm going to train it. I'm going to practice it. There are all kinds of techniques you use for doing this, but the simplest is probably one you learned in math, where you draw a regression line, right? You go, I'm going to plot the variables, and I'm going to draw a line, and I'm going to draw dots, and then that regression is a predictor you can use to classify, right? Logistic regression was a technique we used at Adaptive, one of the techniques we used for machine learning for the immune system. It was just a very high-dimensional version of this. That's why we got it by the FDA, because it was so simple even the FDA could understand, right? Put this, draw a line. Look, that line separates those. Yay, we're brilliant, right? But that's that training. Each point in all of its dimensions has a label, and then you train the system to recognize those dimensions, just like this. And in essence, think of it as the multidimensional equivalent of figuring out where that line goes and saying, now if you put future uncolored dots, you can make a decent guess. Are they in the red zone or are they in the green zone? That actually works pretty well, right? And there are a lot of techniques for doing this, and we'll go into those, but like the obvious one to think about it. Imagine that's a straight line, and then it's just logistic regression with a very simple y, mx, b. Unsupervised learning, there's no colors. What does the data tell you? This is doing clustering, right? And there are a bunch of these techniques, k-means, there are all these techniques for doing this, which then says it imputes the clusters in the data, and then it colors them, and you go figure out what those things are. Oh, well, these guys all seem to be this, these seem to be this. I find unsupervised learning fascinating when it works. And when it doesn't work, you just hit yourself on the head, or you take dimensions out, or you do things like principal component analysis to reduce the dimensionality, right? But this is interesting. The most interesting thing is hybrid techniques, and we do this all the time. In fact, at Fire Diagnostics, one of the companies that I advise, we literally said, well, take all that multidimensional omics, genomics, and multi-omics data that you've got, unsupervised cluster that data. Don't pretend you know what it is, just unsupervised cluster. Then do supervised machine learning on those clusters. You say, you know, it happens that we know what some of those are. Now go and analyze those clusters. You've reduced the dimensionality, and it makes it a more suitable process. The risks to, and this work, actually, this has been spectacular at FIRE, for example. This is a very powerful tool combining these things. And again, these work better when you've got more data. Remember what I was saying about what's really transformational is all of a sudden we have like the entire internet worth of data, or we've got all of the data, we've completely done the complete DNA sequence of every single patient in that clinical trial. That's 3.2 times 10 to the 9th data points per person, right? So all of a sudden you've got way more data than we ever had before. So those techniques that we all well knew about in the 80s can be applied to this kind of thing and have a lot more oomph, right? But here's the risk, and this should be obvious, the old garbage in, garbage out. This is something we used to say a lot in computers when I was a kid and learning it. Poor input data introduce bias. This is bad, right? And this is in fact something that plagues artificial intelligence applications across the board, but it's very easy to understand in this context. If your data set is biased and you're using machine learning to go make predictions, that can be super bad. And we've seen this happen. I'm not making this up. Like there was an early credit score. It was C-score. C-score was a tool that was meant based on actual data to predict somebody's ability to repay a loan. And they were like, look, human beings are so biased, like they might not give a loan to somebody because of their national origin or whatever. Let's have the computer do it. We'll just feed it all the data and it'll come back and make decisions. Well, guess what? The data inputting it was biased by those people. And they put the data in, guess what? The AI then, the machine learning tool, had the same bias. Garbage in, garbage out. This is not a new problem, right? But you've got to be aware of it. Like you've got to think about this, and that bias could be as obvious as that, or it could be as subtle as we're seeing this with AlphaFold now. And I'll talk about that at the very end, but like, hey, it's an AI tool for predicting protein folding. Guess what? Almost all the data that goes into that was of a certain kind of protein that happened to be easy to crystallize and get the three-dimensional structure for when I was in grad school. Almost all. Guess what? The data set's biased. It has limitations in its ability to be able to calculate the folds because the input data is crappy. You need better input data. So, stop 2, people talk about neural networks, right? Neural networks are because they're computer programs that are designed to act like neurons, like human neurons, right? Human neurons work by growing and connecting to one another via synapses, and the neuron like this is connected to all these other neurons, and it will fire its own axon if enough of these neurons light it up. So this is a threshold. It's a little threshold, and it says, hey, once it goes over to that threshold, this fires. Well, guess what this does? This plugs into other neurons, and they fire. And this is called the connectionist view. It's really regarded as correct, but back when I was an undergraduate, there was some discussion about it. But that connectionist comment was, hey, there are trillions of neurons in your brain. All of these connections are trained. In other words, the output that you expect or want is back propagated through the network to set the weights of all those interconnected neurons, such that if over repeatedly retraining this thing, you can get those neurons to properly fire to get that end result that you want. We believe this is in some way the way your neurons work. I will say, we believed to some degree when I was an undergraduate that we were building a reasonably accurate way of the way actual brains work. We no longer think that's true. Brains are doing a lot of complicated things that things like fMRI, functional MRI, are teaching us have to do with propagation of sugars in the brain, propagations of, all kinds of non-electrical connections. The view that we had of how this worked turned out to be too simple and probably not true. However, it turned out to be a great way to program computers to do things that we didn't know how to write a computer program to do. By that I mean, you say, here's the input, all the wiring of these things, and then we set the threshold of the firing based on the output. The arrows are going forward for the output. Remember classification? Yes, no, red, green, whatever. But you also do it, to train this, you do it the other way. You say red, work your way back through the network to set the thresholds, and you repeat that till it works, till these inputs match the outputs that you want. Now, I say this, now this is a super simple example, but it's sufficiently large, you can do things like handwriting recognition. That was kind of my project when I was a kid. So these actually turn out they're very effective at classification problems. They start to run into problems, though, because you can probably see, you just reach a point where, it's a very steep thing, and it's like right at the top, and it's as good as it gets. You can't really make it any better because there just aren't enough connections. That's the trouble we ran into back in the 80s. We just ran out of compute. We just couldn't make the thing big enough to do really interesting things. However, fast forward to 2012, thank you, Jan LeCun. Jan LeCun discovered deep learning in which he took sets of these. Each of these neural networks had a job. So this job is classify these pictures. Well, fine. First you start very broadly. Find local shapes or local patterns. Its job isn't to decide who's who in that picture. It's to say, hey, I kind of have figured out the rough patterns. I don't know what those patterns are. They're just blobs in the picture. And in this case, you can even see, this is grayscale. It got rid of the color data. The color data didn't need it. Now those patterns are fed into a different new neural network that associates those patterns with facial features. That's an eye, that's a nose, this face is turned, right? And then finally, the pattern of those things is fed into something that looks to compose it into a face, given its turn, it's looking up and down, it may be wearing glasses. And then finally, once the faces are figured out, it's handed to the output layer that says that is Sue. Deep learning is just adding each of these stages and segregating them and then figuring out what the proper handoff is. It's an art to this. It's not easy to do, but it's exquisitely powerful. Deep learning was what enabled us to make Deep Blue and win at chess. No human being will beat a computer again because of this. Yes?
So what is the output layer you're seeking to get here? It may be just like, what are the men, who are the women?
No, this example is in this paper here. This is an identifier of people.
Okay.
So this is Sue. Find Sue in this diagram. But it wants other pictures of Sue that it didn't see before. So you trained it on a training set.
Right.
And then you wanted a discriminator. Maybe this is yes Sue, no Sue. Those are those output neurons. It's actually kind of a fun paper in this thing because it walks through this process pretty clearly. Yeah, that's a great question. I've said this before, I'm just going to keep repeating it. Why this works is we have near infinite compute and near infinite storage. Like, our brains have 1 trillion neurons. If you're going to do a brain-like thing, you need just a stupid amount of compute. But with that, you don't need to do anything particularly technically new. Like we were doing this in the 80s, we're able to do it. So let's talk about adversarial. This is where it gets a little bit more complicated, right? Adversarial systems are basically trained by having a computer play a game against itself and do that 1 trillion times. AlphaGo, this is the thing that now beat Go. People are like, oh, computers can play chess, fine, but they're never going to beat it at Go. It took about 5 years, and they're like, no, yeah, we could do that. But we used a different tool. This is super neat, and this is so brain-bending. I absolutely love it. Generator and discriminator. So you have think of it as 2 computers. One's job is to make fake data, and one's job is to figure out if that data is fake or not. And then you have a set to test. So you have a training set. These are the actual things. And then you start with random noise and have the generator make things that are like that. And then this thing has to figure out, is that a real digit or is this a fake digit? And now you repeat this 1 trillion times. This improves, using things like deep learning. And in fact, AlphaGo is a deep learning network. The discriminator is a deep learning network. The generator is not. It's a generative network. But again, you go build your neural network and you just keep training it. And you keep teaching it. Bzz, nope, that's fake. Bzz, nope, that's right. But it gets better. And if you do this 1 trillion times, remember what I said about infinite compute? You do this enough, it'll get really good. Here's the interesting thing. Usually people then throw the generator away. And they're like, now I've got a discriminator that's super good at finding. We've got a company that we're looking at that uses generative techniques to find faults in video of train wheels. It wants to know, just a video picture, taking a snapshot of a train wheel, is that train wheel likely to fail? And the way they did it is they had a generator that generated zillions of fake train wheels, data sets, and then a handful of real wheels, which either worked or didn't. And then the discriminator got very good at figuring out which the real ones were. And the belief is that what it's learned to do is extract subtle things from the data set that we may not have really noticed that make the distinction between what really matters for something to fail and what doesn't, right? But here's the cool thing. It turns out that you can take the generator and go do interesting things. So for example, imagine for a moment that I want a device that discriminates between cats and dogs. They actually did this, right? Great, I have the generator starts making fake cat pictures and fake dog pictures, and the earlier ones are like this, and they don't look like cats or dogs at all. But after a while, it gets pretty good at making things that look like cats and things that look like dogs. Now you have a thing for making realistic looking cat pictures. All of the work that you're seeing, all of these generative AI things, and I'll talk about simulated diffusion, about how this really works, are literally that half of this. Oh, I can make a thing that looks like a unicorn with wings at the top of the Empire State Building, no problem. Fake, real, right? But it just turns out that the generator is an interesting piece of software itself. The thing here is just, hey, you're just trying to maximize my probability of being right, and my probability of being right, let them fight. We are using this, like we're actively using this right now in one of our portfolio companies to analyze very large data sets, to build discriminators. Our real goal, frankly, is not so much building a thing that can decide yes or no, but mostly figuring out what is it that's important. This is something you hear people talk about, explanatory capability. Like a really important quality of good AI systems is high explanatory capability. That means you can go into the system, it's not just a black box going yes, no, why. If you build this kind of system right, you can go look and say, what are the features that are causing this thing to do this? And then from a science standpoint, go dig into those. Why is that? And again, if you're looking at these massive multidimensional data sets, like the whole human genome, or worse yet, the whole human immune system genome, this kind of tool is used for that. But I love the idea of just building a thing. It's like, your job is to fake you, your job is to figure that out, fight for 1 trillion iterations, and then we'll come out with the best. What this looks like is sort of fun, right? And let this cycle through. It's very quickly, it starts with fuzz at the beginning, and it very quickly starts making digity looking things, right? These things look like real digits really fast. The generator is an interesting and fast tool, right? Pretty soon you get to the point where that generator is pretty much indistinguishable from a handwritten digit. I called this step 3.5 because remember the generator part? Remember making pictures of kittens? You've all seen this, I think. I mean, everybody's seeing these. What if the Wizard of Oz was, made by the Star Trek producers or something? Those tools, this is utterly unpredictable. So the way it does it is it starts with a description, right? And we'll talk about the text encoder in a minute. And it adds noise, right? It adds noise. So it starts out with the input image, cat. I want more cats. Adds noise to the picture, right? The trick is that you want to very subtly and slightly add noise to the picture. And then you build the training model to predict the image out of the noise, right? So if those steps are small enough, you can fork it and start to generate a new picture. And that's because, in essence, by adding noise to the picture and forcing the thing to discriminate, can you still tell what it is? You're extracting things that make that picture what it is. What makes a cat look like a cat? What makes a cat look like a cat is very gradually obscured by the introduction of noise, and you train your model on those very, very fine increments. And then that trained model allows it to fork out and create images which look kind of like that, but not exactly. And if you've seen AI-generated images, you know exactly what I mean. I'll give you an example. You can always say, this will probably not be true forever. It may not be true even anymore. But I used to tell AI images by seeing if the fingers were either obscured or there were too many of them or whatever. That was my key. Often you could tell because somebody's hands are behind their back. Please draw your picture with the hand behind the back. And the reason for this is that the noise image, when you get multiples of these things, it's not really distinguishing how many digits you've got. It's just got that kind of digit-ish noisy image. Imagine the overlay of noise, obscuring digits, fingers. You're like, yeah, I guess that would do that. Look at AI pictures that are generated from now on, and just imagine for a moment that what you're doing is you're kind of squinting your eyes. If you look really carefully, all of a sudden you're like, no, it looks a lot. This, to me, is one of the most shocking and surprising things that works. Slowly add noise, train the thing to sort of distinguish between what you can see and what you can't, and then use that to build a generator. The text encoder I said we leave out, we're going to talk about in a second, because that's a language model. But that language model says, hey, take text, turn it into an encodable, you'll hear me talk about a reference model, and then you feed that to the image encoder. Remember, each of these images that are fed in are like cat's face in living room, I don't know, whatever, some image description. At the same time that you're encoding the context of the image, you're also associating the words that go with it into a language model. And we'll talk about a language model next. But like this is a real thing, like Corgi playing trumpet in cartoon style. Like what? Why does that work? These things solely work because there is so much data and so much ability to do compute. Every single image of cats on the internet is fed through that thing such that it knows exactly what distinguishes one frame from the next as we add more noise and where those things get mixed up. Where is this blurry, ishy image look like all the other cats and then fork off? If you imagine this as a big graph with all these cat pictures that slowly glom together as you add more noise, and the train can shift at those points, and you end up with a different looking cat, that's how that works. Half of the fun of AI is you're like, how does that work? I'm not going to go over the detail, but I wanted to add it because this is incredibly complex and sophisticated. This is the sine qua non of AI right now. This is transformers and large language models. If those of you who watch the news, GPT-4o was just released. They then now have it doing video. Anthropic has a model called Claude, which is probably the best language model right now, probably better than GPT-4. We're all waiting for GPT-5 because then it'll be better. My other kid works at Adept, where they're building an action model that looks at how computers do their tasks, right? Here's the key to unlock this, I think, for you if you don't know a lot about language models. Think of a language model as, imagine that you took everything Jane Austen wrote as text. And you wrote, you just took each word and you said, okay, I'm going to build a database that simply counts how many times does from word X go to word X plus 1. I don't know, like if you did that over and over, it is a truth. You're right, Pride and Prejudice, it is a truth. It is, well, that's probably pretty frequent. So imagine that there's a database that goes, it then is, and it's this often. It then was is this often. Mr. then Darcy is this often. You just do that. Now, if you imagine for a moment that you build that from all of Jane Austen's books, and now you just go build a computer program that starts with a word, it, you tell it, and then say, go pick the next word at random based on the frequency in Jane Austen's books. Anybody can write this computer program, and I would encourage anybody who knows how to write code to just do this. It's a fun thing to do. It's like 10 lines of Python. It's rather surprising, because you can go get Jane Austen's books off of Gutenberg and just feed it. It is. It will literally spew vaguely grammatical, kind of weirdly, like, I don't know, early 19th century English. It doesn't mean anything, utterly doesn't mean anything, but it's a little strange. If you go back now and go, now I'm going to look at the 2 words before that. These are people, I call them n-grams, right, or a bag of words. I'm going to look at it is, then the next word. Your database gets vastly bigger because there are a lot more possible combinations. If you do 2 words, it starts to sound intelligible. By 5 words, you're like, Jane Austen could have written that. Like literally, it seems to make sense. You have to look closely to figure out that it is not. And frankly, if you train it on one novel, because it's not mixing the characters up, by 5 words, it's pretty reasonable. Now, that's not a large language model, it's a small language model. But the fact that it works, the fact that you as a human being reading that text are like, huh, yeah, kinda, ish. Now shift gears and say, we're looking at the multidimensionality of that problem with the entire internet as its text corpus, and that the metadata associated with it, right? So they're doing it a little bit more complicated than I'm making it sound, but not much. Where did that come from? What does the header text look like? Are there any tags in it that get a little bonus, a little push up, right? That's the way these training things work. you've got a big data set now, which is very high dimensionality. This isn't just 5. This is like long, right? That big high dimensional data set will tend to cluster things that mean the same thing in the same place in this high dimensionality universe, right? So your text creates vectors. Just think of a vector as a dot in this place, and all the things that are kind of about that dot are ish there. Now, if you give it a prompt, imagine that prompt for a minute is just complete the following sentence. You know, I don't know, all families, unhappy families are different. Finish that. If you go give GPT that right now, it will literally give you the beginning of Anna Karenina. It really will. How did it know? Does it know Anna Karenina? Like, what the hell? What's going on? No, it just turns out that in that space, that's what that's about. But the weird thing is if you back up and give it a prompt, that prompt maps out fairly comprehensively into words that are in that space, and it will generally and somewhat reasonably answer it. Now, the real magic in this is in the tuning that I was talking about. It's the weights that you give that metadata. It's the weights that you give the structure. But simply, that's all that's going on. And this is a big caution, right? The big caution, you know how people talk about hallucinations? Anybody who's played with GPT is like, what? GPT's completely wrong. What's going on here? Like, what is this hallucination thing? The hallucination thing is, it's getting up into that word space generally, and it's giving you an answer which is like the scrambled, Jane Austen book, reasonable, but just wrong, right? Reasonable, but wrong. Now, there are techniques to minimize that, but I always say, at least now, and maybe this won't be true, I'd say in a decade, maybe next year, maybe next week, treat any of these language models like your college roommate who always seemed to know what he was talking about and very confidently would give you answers, and they always turned out to be wrong. We've all had that person in our life. Like, what the hell, really? Why did you think that? Well, I don't know. That's how you should treat the answers that come out of this system. It sounds good, it's very clear, it's well written, but you better make sure it's right. Now, there are techniques actually to use the language model to make sure it's right, by the way, but you have to do it. Maybe you won't have to do it in the future, but like, there are a bunch of these, right? GPT, Claude, Persimmon, there are like a zillion of these. There probably won't be a zillion of them forever. I'm sort of infamous for saying I thought they were going to converge. I thought by now, I said by the summer of 24 we'd converge. We would really be left with just GPT-4 or 5 or N, OpenAI. Weirdly enough, that hasn't happened. We're seeing Claude is a little better than GPT. If Claude stays better than GPT, that's going to be interesting. But what's turned out is there are a lot of narrow things which have narrowly gone to attack very particular and specific problems. So, I don't know. I think this is super cool. This is, like I said, this is kind of what's it right now. I'd say there's just a bonus stop before we leave this. A key way to apply many of these models, but we'll use large language models, is something called MetaGPT or AI agents. What you do, and I like this here, is it's like you have a prompt. You know, people talk about prompts as what you ask the agent. What you do is you set your agents to do particular tasks, as if you were assigning a person to do it. A good project manager doesn't just go, Bob, Sue, and Lou, go all do the task and come back. You go, now look, Bob, your job is to do this. Lou, your job is to check Bob and make sure he's doing it right, and then your job is to write it up. A technique is and this is done just by prompt engineering, literally say, I have a task for you, go generate this thought piece. I don't know, go give me a summary on the status of AI drug discovery. Now your next thing is you say, okay, your job is to take that and find a reference for every assertion that's made and put it in the text. Now your job is go check those assertions and make sure that they're correct. Turns out that's a pretty good technique. There are other things that you can do, like you can give it a context. As somebody submitting a document to the federal government where you'll go to jail if it's wrong, do the task, right? You can literally, or I think I was saying when people are coming in, like a technique I literally use all the time is, hey, ChatGPT, go figure this out. If you don't know the answer, please say I don't know. If you cannot find an answer, please say I don't know. You're literally telling it, don't hallucinate, just say I don't know. That one thing has greatly improved the quality of what I've gotten out of language models. That one thing. If you don't know, say I don't know. But the cool thing is reproducing the kind of a software engineering team. And this has been done for software engineering actually pretty effectively. We did it at Adaptive. but we've got a project running to do this for Hollywood scripts. And not the interesting part of Hollywood scripts, the really boring kind, like write a project plan, generate a budget, give me a shot schedule, like things nobody wants to do. You can do that. Like, really, you can do that. Again, it's one of these surprising things, but by deconstructing the task into a series of agents, you can both check the work, better yet, you can have the AI check the work, but you can end up with a team that looks a little like this that can actually do the task. So kind of as we've gone through this, we've talked about applications, right? There are a couple that I'm just going to hit quickly because I think we're all familiar with autonomous vehicles. I even did it twice, so that was clever. Should have had AI check this. They're very important. Autonomous capital V and little v are different. But we all know AVs, right? We know speech recognition. We're actually seeing it all the time. Machine vision's actually been around for a while, right? Life sciences. You're hearing probably a lot about artificial intelligence drug discovery. We've got a couple of companies we're looking at right now that are doing very interesting things. And again, this is almost a perfect fit for AI. Much more data these days in the drug development process. Having machines narrow that down and improve it is a good application of AI, as is, for example, getting all the clinical data, which is often a big giant mess. Great application for language models. It's either that or very bored graduate students, and I've been there. But almost more interesting to me, frankly, and we just had a meeting about this at Pfizer, and AI drug development. For those of you who don't know, my colleagues at Leerink know this better than anybody, the real spend in drug development is not in the discovery side. It's in the early, let's call it late stage preclinical and clinical development. That's where the money is spent, like doing all the clinical trials, getting the documentation ready, getting it to the FDA. I think the most interesting applications for AI right now are in that. Now here's the funny part. I've also been talking to my friends at FDA who are like, Mark, God, we need to get AI to help evaluate these applications. So we've got the pharmaceuticals who are like, man, we got all this data, but we got to write these ridiculous long documents for FDA and the person to read. We can use AI for that, right? And then I go across the street to the FDA and they're like, God, we get these giant documents in writing from people. Could we just have AI read those and give us the answer? I'm like, how about if your AI talks to my AI and we could just skip the middleman and not write these ridiculous documents? But it's very interesting. Healthcare, increasingly as a way to provide frontline telemedicine. I've got a colleague who's doing that right now for badly underrepresented groups. These are folks who can't get reasonable, particularly mental health care, right? They just can't get it. So there are certain things for early stage triage, particularly for substance abuse prevention, that they've clinically proven, like they've done validation studies to show that interactions through telehealth with a machine improves the outcomes. Is it perfect? No, it'd probably be better if a human therapist were doing it. Guess what? We don't have enough of them. Get that underserved population in there, get them using the tool. The last I'll mention, and one of my kids is working at Palo Alto Networks, leading a cybersecurity AI team. The bad guys are using AI to write phishes and all this other stuff that the IT groups are trying to deal with. And those phish emails are getting really good. Why? They're using large language models to generate those things. They know all about you. They can talk just very knowledgeably. They can probably carry out a long email conversation with you. That means that the other side has got to get better at combating that. And again, using artificial intelligence, for example, to figure out what's spam and what isn't, what's efficient, what isn't, but also better network security is an application for AI. And of course, on the warfighter side, this is a big deal, figuring out how to fight. Kind of we're watching this unfold in Ukraine right now, unfortunately.
Sorry, I have a small question.
Yes.
Has anyone considered or tried to use AI as to see the bad AI? So there are bad actors who are using bad AI. By analog, we know that mosquitoes are often pests. I know there was some work that's recently been done in order to try to replace, to release mosquitoes in the wild that are genetically engineered with certain defects.
Yeah.
In order to crowd out the other mosquitoes. Is there some way to almost give the bad AI folks something which has an embedded tell, so
Yeah.
good AI can detect it more easily?
I have a colleague you'd love talking to who led the security team at Chrome when Google launched Chrome, who's doing an AI honeypotting, which is literally exactly that, right? And it's saying, in some sense, how can we figure out who the bad guys are by attracting them? And then can we inject markers or use their markers? Because they're going to go to that obvious honeypot, get marked. and then communicate those markers back out.
Or put it in the market somewhere, and we know like who's going to really be using this, and it gives the tell that way because we've seen it.
And in fact, I'll even go one further. There's a company, Binarly, which is doing really interesting work where they're using a language model. Remember, we're talking about large language models kind of defining the space of like reasonable questions of a given type. But again, you may be familiar with this. There's something called supply chain management, right? SBOMs, right? This is a supply chain bill of materials, right? You want to secure your software bill of materials the way you secure your physical bill of materials. In other words, if you've got, your firmware chips for your router are coming from an insecure place, your routers are definitely, because we all suffer from this. Like IoT is just a giant mess because of this.
Frankly, a secure place because a lot of them are also questionable.
This is my whole point, right? So the problem is that usually the way you do these supply chain things is you validate the source code. Some human being goes and looks at the source code and makes sure it hasn't been screwed with. But you generally can't get the source code for most things. They're just all open source or it went from some vendor or whatever. Binarly goes, well, we're not even going to bother. We're going to take the binaries. That's where the name comes from. We're going to take the binaries. We're going to reverse compile those binaries into fundamental bitwise operations, the simplest possible way. Human beings still couldn't read this. But things that do the same thing look roughly the same. You know where I'm headed with this. Now you project those into a language model. And you say, here's where things that operate properly to do that live. And this is over here, bzzzt, punt, or at least have a human being look at it. Right? So this is literally what you're talking about. It's just going, I'm going to let the bad guys put the marker in, and then I'm going to find it. Punks. I used to run a cyber security business when I was at Booz Allen, and it gave me heartache. So let's just talk briefly about artificial general intelligence. People talk about AGI, right? I love this commercial if you've ever seen it. This is the robot at the coffee shop trying to do CAPTCHAs, and he gets mad. What is a bicycle? He lasers it. This is one of the reasons I think it's kind of funny. Artificial general intelligence is machines that have human-like cognitive capabilities. We used to call this hard AI or strong AI when I was back in the day. There's sort of an interesting thing where people often say AGI, but what they really mean is artificial superintelligence, like where computers are smarter than people. The technical definition generally accepted is computers have human-like cognitive levels. They can do things that humans can't. And remember we talked about the Turing test as kind of like a bad test of this? People generally regard a good test of this as if the machine can solve a human problem in unexpected circumstances. That's the difference between strong AI and narrow AI. Narrow AI is, I don't know, Deep Blue beats everybody on Earth at chess. That's pretty impressive, but it's narrow because it's playing chess. If it can solve a general problem unexpectedly. Hello, we're going to play chess today. Oh my God, your car won't start. A human being who comes to play chess with you might have a crack at figuring out why your car won't start. Deep Blue will not help your car start. If you ask it that, it will just, I don't know, that doesn't have eyes. But that's the definition. Now, the reason that superintelligence gets a bit confused with AGI is scale. Let's just say for a moment that we achieve human-level cognitive abilities. In other words, a thing is a thing that can do what a person can do reasonably. We'll just assume that. But hardware is getting 10 times faster every year, and storage is getting 100 times cheaper every year. So suddenly, at very least, you've got much faster human cognitive capabilities that are getting much faster. You're not getting 100 times faster in a few years. It is. So this is why I generally say I think it's a little bit of a bogus distinction. AGI, if you can make human-level cognitive abilities and you just wait till hardware gets better, you have superintelligence in a pretty short period of time. My point is, A, is this even achievable? And B, does it matter, right? Remember that thing I showed you all at the very beginning of this that's like OpenAI is like, dude, we're working on AGI. Money may not matter anymore. They believe they're probably the most intensive and well-funded AGI research in the world right now. And the reason they're doing it isn't they want to make money at AGI. They don't actually really think they're going to make much money at it. And they're spending like drunk idiots right now. The reason why is they feel like they have to get there first. That's what they believe. Again, I don't even have an opinion on it. I'm not informed well enough, but that's why they're doing it. This is why these guys are absolutely throttle all the way down and figure this out because they want to get ahead of it. Expert opinions really differ as to whether this is even possible, or more importantly, does it matter? Remember the quote about the submarine swimming? We're going to get better and better and better at narrow AI problems. And what constitutes narrow is going to widen. We're already seeing this, right? You could probably have, I don't know, like GPT-4 play a decent game of chess with you. I bet you could. I've never tried it. I should do this. But I bet you could get it to play a decent game of chess. And in the middle of that game of chess, you could say, Chip, my car won't start. What should I do? It probably could give you a reasonable answer. So kind of what's narrow is getting a little wider. Is it going to behave like a person? Probably not in the near term. And there are lots of reasons for this. I'm a biologist. I tend to think about neuroendocrine flows, emotions. Why do people make the decisions they do? It's very complicated, and we absolutely don't understand it. We absolutely don't understand consciousness at all. I'm not even sure we'd know. Whatever. But that's why I say expert opinions differ. That said, like OpenAI is making a bet. You saw in their funding documents, right? I think computers are going to continue to widen what constitutes narrow, but to human level, you want my opinion? I'll say not in my professional lifetime, but I'm 60 years old, so. So what does this mean, right? Like, geez, man, what does this mean? My absolute favorite poster. Why should AI take the fun jobs of artist and musician and all the really fun stuff that we want to do? Like, I think that's a really good question. Where AI can really shine, I think, is doing all the boring crap. Remember what I said about like figuring out how to do a shooting schedule and a budget for a movie? Nobody wants to do that. Believe me, creatives have no interest in that stuff. I think it's happening. I think, frankly, if your job is like, I'm drawing all of the keyframes as an animator in a Disney movie, that job's already gone. They have not been growing their animation team for years, long before AI did anything. It's just, turns out that's a thing computer does pretty well. The downside, and we used to have this conversation when I was at Leerink, as more and more of these capabilities start to come out in banking, like where more and more of these sort of ground level analyst jobs can be done by machines, associate jobs, where do we get our analysts? Where do we get our experts? Where do we get the people who really know this stuff? That's how you learn it. Absolutely the same thing with software engineering. The really boring software engineering jobs like commenting code, writing unit tests, like building the really basic porting from one language to another. We all learned software engineering as early software engineers in the boring crap, right? That's terrible. Nobody really enjoyed doing those jobs. And in fact, even today, things like CodePilot combined with GPT-4 are very good at those tests, probably better than people. They're certainly better than people because they don't get bored and play Fallout 4 or something. Like, the problem is that that's how you get good. And to get good better than the computer, you have to do that. So I think there's a huge open question about like, what do we do as an organization when on one hand, we're like, man, we could do this a lot cheaper if the computer did it. Yeah, but then how are you getting the people who are going to make the strategic decisions going forward? We talked for a minute about bias. I think this is really a big deal, right, as we build AI systems, because they're going to have intrinsic bias. There's almost nothing we can do about it. That's because the data is so big. We need to get very good at detecting bias and managing it, right? Being willing to call it out. And then there's lots of other things. I mean, geez, privacy. We used to have this thing we called it the Ray Charles rule. And there was early on in healthcare, when we were developing HIPAA, yes, there was a time when HIPAA didn't exist and we had to figure it out. We used to talk about the sort of safe harbor data that you could safely share about a patient and not identify them. And if you took certain things out, like, well, the zip code, it's okay if you share the zip code. A lot of people in a zip code. You could share their age, and you could share their, some basic information about their national origin. That should all be fine, right? And A.G. Bertelstein, who's like brilliant jurist, said, sure, but what if I say, as an African-American man, 89 years old in 90120, blind? Who is that? It's Ray Charles. That was it. Like, you've just identified that person with 4 pieces of data that you just happened, and you could literally go look it up. Her point was there is no subset of data that a sufficient data attack can't identify you. You know what's super good at taking all kinds of uncorrelated information and figuring out who you are? AI. Like, again, I think, look, these aren't long-term, oh my God, the Terminator is going to take over issues. These are issues that we're dealing with right now. We really think about. But, I mean, longer term, right? This is transformative. I saw this with my own kids. You know what was really great at teaching my own kids like to do things? Computers. Because they didn't get bored, they didn't get frustrated. They would just keep telling the kid over and over that thing, and they made it fun and interesting. Like, both of my kids are hardcore, like, technical people now. Computers largely taught them that stuff. And that was, I mean, those weren't even good computer programs for teaching people. Modern AI of the generative type that we're talking about can create micro-worlds with problems that are almost infinitely complicated and coach somebody to a solution and then do it again and again and again and never get bored. Today. It's not the future. This is today, right? Space exploration is an obvious one. They're always an early user. We're seeing this at SpaceX now. Like we're seeing this at NASA. Space probes are getting better and better, like really better and better. What about when the probe is sort of human level intelligence? I mean, who wants to send astronauts to places? Human beings are terrible travelers in outer space. You know, really good robots. What if those robots don't need to call back home all the time to do something? This is, I think, transformative potentially, particularly when you start going a really long way away. People know about like breakthrough starshot, right? A whole bunch of like, I don't know, like pill bottle sized robots on solar sails fired by laser to Alpha Centauri. Boy, they're not calling home. They need to figure out their stuff to send useful information back. This is an enabler. But all of this stuff is seismic and it's changing very quickly. We had a great conversation before the talk about, well, geez, Mark, what would you invest in? See that thing before? I don't know, right? But like I said, well, I'd be looking at what does AI consume? Chips. It consumes resources for energy. It consumes these things no matter what. What is it used for? What can be uniquely done with AI that can't be done today? Materials science. A number of these AI drug development things that we talked about. There's certain things that are problems that are literally undoable without AI. Invest in them as they become doable. And then what I think is the riskiest thing from my personal perspective is this just going to widen inequity, right? Inequality is already bad, right? As machines become more and more able to do things, what are we doing to make sure that it's equitably shared and we don't just end up with like a very small handful of people, which is what we've done so far, who break in all the wealth and everybody else is like just, I don't know, whatever, eating dirt. That we've got to figure out. And I think we're going to be forced to figure it out, frankly. I think this is the thing, because what it's going to disintermediate aren't a few manufacturing jobs here and there. It's going to disintermediate the entirety of the sort of typical white-collar worker. We have to get ahead of this. This isn't going away. Thinking about what to do is really important. And I wish I had a pat, trivial answer. I do not. But it's something we need to be considering. And then lastly, like I mentioned this curve, the Kurzweil curve, right? And that curve is just how long is it between innovations? That curve, almost no matter how you project it, is this shape. We are at the hockey stick moment right now. The innovations are coming so fast. This isn't like my entire career. This is like last week, something amazing happened. That turn up here, and we're seeing this very clearly here, people talk about like, hey, at what point does it just become unforeseeable that we literally can't figure it out? I actually think we're there. We're not past it. I just think we're looking and going, you saw the OpenAI funding documents. They're assuming that. They're literally, well, dude, I don't know, singularity, and I wouldn't invest. Like, if you're investing, you're not going to make money after singularity. Do I think this is something that's like proximate, that's going to happen tomorrow? No. I think what's going to be weird is like all of us are going to look back and we're going to say, oh shit, that happened. We're not all going to be like, look, it's happening. Like suddenly things are going to be seismically different. The one thing that's happening is, and I see this in my own kids, they're getting so good at being flexible. I look at my parents. My dad expected to be in the same job his whole life, and he did. He was, was in the military, and then he was in title insurance, and he stayed in that for his whole life. Got a gold watch. He was kind of mad at me for shifting jobs all the time, and he's like, when are you going to get a real job? What do you mean by real job, Dad? One you stay at. And I'm like, never, right? Like, why would I? I'm a computational biologist, Dad. I look at my kids. They don't even anticipate they're going to stay that long. They're like, yeah, I don't know. Technology's changing so fast, I could be doing something completely different. So I think a little of what's going on is we're training people to just expect this. I think they'll be less disrupted by it. They're still going to get disrupted by it. Maybe a little less. So last, hey, I always like to have this slide that just goes like, well, what do we do? AI literacy, that's why I'm here today. Literally, this is just going, this is what this thing is. These are sort of practical understanding of what it means. understand the language so you can make good decisions. Because frankly, being an informed electorate, like you guys are going to advocate for things, you're going to vote for candidates, you're going to do all the things that we do in a democracy, know about it. I always say promoting STEM, like the more people that just understand this stuff, the better. I'm a huge fan of like what I like to call it being B+ engineers, partly because that's what I am, sort of fair but not great. But like everybody needs to be a fair but not great. Everybody should sit down and learn how to code. It's fun, highly recommended. But B, it's just understanding. You don't need to be the world's best coder. You need to be like Steve Wozniak or something. You just need to get it. What are computers doing? What are they capable of doing? Like making sure that people are talking about this, I think is important. Bias. This is what I think about now. That's the most proximate thing. There are other things, but boy, that's the one I really watch now. And then I'd encourage everybody to just play with it. Sign up for GPT, play with it. See what it does well, see what it doesn't do well. It's really pretty easy and shockingly useful once you get used to using it. The best thing is you get an idea of like, it doesn't do everything perfectly. It's kind of crappy. Literally realizing and knowing when it's crappy. And the best thing is you get to feel for what the output looks like, and then you know when people are sending you things that were generated by AI. You're like, oh, I'm on you. All right. I know it took a while. I'm sorry, but it's fun to go through this stuff. Happy to take questions and answers.
So what happens if, you talk about, well, everything is going through an adoption curve, and we're in this up phase for AI right now. I guess a question for Two Bear Capital is like, what is the bearish thesis on what is not going to work in the near term that causes this to pull back?
I'll give you the two bearish thesis. Does anybody else think two bears? It should be two bulls. It really bothers me. And I get told by my colleagues, they're like, we're in venture capital, not Wall Street, Mark. I'm a public securities guy, right? So I've got kind of two answers to this one. All right. One, direct investment in AI, I think, is crazy right now because it's so frothy and so overvalued that we couldn't even invest in it if we wanted to. Adept AI, the company my daughter's at, took $500 million of capital. There were 35 people there at the time. $500 million of capital. Now they're going to spend that all in compute. But like, we couldn't spend $500 million. We don't have that kind of money. So I think a lot of the foundation model, the real kind of basic AI stuff is just overpriced, and I wouldn't do it. And again, it's very risky not because it won't work. I think it's going to work, but picking the one that's going to win, probably OpenAI if I were to bet, but you can't really invest in it, so not a great thing. What I would do is step one back and say, what can you invest in that would retain its value, even if we go into another AI winter and we blow the tires out? Yeah. We've got a portfolio company, TileDB. They build the fastest vector database. This is another Michael Stonebreaker company. He's a guy who took the Turing Prize for Postgres, right? MIT professor. Fastest vector databases. You remember those vectors we were talking about that hold all of the data from the internet? The thing that makes Adept AI's investment require $500 million is they'd need so much compute. If you can reduce the cost of that compute by having the vector database that holds those vectors be a 10 times faster or a tenth the cost, that's huge. The nice thing is this whole AI fad could just go back into another AI winter like the polar bear hibernating. That database still retains value because it's useful for a lot of other things. So that's kind of my hack, and you can tell this is why we're investing. The third thing is we're investing in companies that can use the current version, prove working, AI to solve problems. Cybersecurity is an example. Like we have a company that we invested in that's like, yeah, there's this problem we couldn't solve without large language models. That already works. We're not making any bets about what might work. I think that's risky. But it's kind of and that's an early stage VC answer too, right? I mean, none of these guys are anywhere near being public companies, right?
How much do you think is going to affect the brain of human beings of saying, I already see it, I'm studying, and I use ChatGPT to answer some of my assignment questions to get a structure or anything, and I get so lazy, I'm like, well, ChatGPT is going to do it for me, and it's, how do you think it's going to, in the future, affect people working together, people working on solutions, if AI can do it, and then ultimately, if AI obviously gives you a solution, and it's been proven right like a few times. People trusting ChatGPT, not or like even an average person using ChatGPT as Google, you know, as an informative source.
Yeah.
And not being, because I don't have the knowledge, you know, not being 100% sure if that's 100% right, and because it's proved me right in the past, taking that as a right answer and not even knowing if it's 100% true.
I think it's an amazing question. I mean, I think there are three answers to it. One is your first answer, like, what is that doing to people's brains, right? Like, we've learned to do things. I mean, and I say we, like, I tried to explain to my kids what a card catalog was. You can imagine how that went. My kid looked at me, amusingly enough, both of my kids in AI, and they're like, how did that even work, Dad? Like, no, that's what we really did. Like, I think she thought I was making it up. So there's certain capabilities that, like, we're not wiring the kids to do now. Forget ChatGPT just because of Google, because of basically your ability to pull your smartphone out and get at things. I think that's making a fundamental change. And I think there's some papers on this where they do fMRI and they look at how people solve problems. If you look at somebody my age and looking at how I solve problems, it's quite different than the way my kids do. And that's not AI necessarily, but I think AI is going to make it worse. So that's just the explicit answer. Is it changing the brains? Absolutely, and there are good papers on it. There's good evidence. B, like, what does it mean for somebody's capabilities? Like, what are they able to do? You know, it's almost as if everybody is in a world now where they're surrounded with people who have the answers to everything, but they need to learn to differentiate between what's reasonable and isn't in some way. And I don't know the answer to this, but like there's almost a different technique that people are going to need to be inoculated. Think of it as like a vaccine, right? You need to be vaccinated against this because to your point, like, hey, it gets it right a couple of times. You're like, dude, I'm just going to do it more. Being able to sort of be critical about what you're getting, know what to look for, have ways. And those ways might include your own work, or it might be giving the right prompts or having the thing check itself. That's the thing I actually do when I use that. I give it prompts. My classic example is, hey, if you don't know, say so. In your prompt, like, I need you to look this up for me, and if you don't know the answer, it's okay to say, I don't know. That's the prompt. So there's certain prompt engineering techniques that you can learn to use, well, make that better, not perfect, but better. You can also program another agent, remember that agent thing I said, to go check. So there's some things that I think young people are just going to learn either the hard way when they turn their paper in and they get an F, or they just go, that doesn't seem right. The last thing, and this is speculative on my part, but I'll sort of say there, I think that we, in some sense as a species, are evolving into a hybrid entity where part of our brains are silicon. It just happens it's on a phone outside of my brain right now. Like, I just think that we, even today, and probably not even recently, Pierre Teilhard de Chardin had this concept. He was a Jesuit monk who, weirdly enough, was a paleontologist. I've always thought that was strange. French, right? Like turn of the century, so a long time ago. Not the recent century, but the one before. He had this concept of the noosphere. And his idea was that there's this sort of conceptual place where it's the realization of all of the thoughts that are shared by people. And it was a conceptual idea, not a physical one. They're like, hey, where'd all those ideas go? Well, he had this idea of the neurosphere. It's everybody's ideas that we could draw on. The weird thing is the internet kind of implemented that. Like, hey, this is where all of these ideas go. It's just weird that because of things like Google, we can get at it. Yeah. Maybe this is just the kind of techno-optimist because that's the kind of guy I am. I just think we're evolving as a species fast and that we're already a hybrid species, partly electronic, partly communications. I mean, depending on how things like whatever, Neuralink and whatever turn out, that could very quickly just be like, look, there are people and maybe most people who are basically fully hybrid. Like there are going to be people who are like, oh my God, that's the worst thing I've ever heard. I'm going to go live in a cabin and farm vegetables. There are people who are like, I want to be an immortal space robot, and that's where I'm headed. And I think this is a strange thing about the human species, but I mean, pending us not destroying ourselves in some way, I think that's where we're going to end up. Not everybody, but somebody's. If you think that's a good thing or a bad thing, it's a personal thing, right? But yeah, you're right. I think it's already changed our brains. But it's an extraordinarily good question. It's probably, frankly, the most important question of this whole thing. Because all of this is just how it works. How did it work? Where did it come from? It's sort of boring. Your question is like, hey, what's the impact on us as a species? Good or bad? Both? Like any technology? I mean, I literally am sure that before fire, there were people who were like, look, I got fire, and look at all these things I can do with fire. And like, dude, you know, you're not going to be good at just chasing the prey down anymore or whatever, or farming. All of these things have had good things and bad things. Every technological thing we've done. So that's a terrible answer, but it's the only one I got.
Thank you very much.
Yeah. Yeah.
I kind of wanted to ask you about your kind of take on regulation. I think as a young person, my perspective is that the U.S. government tends to be run by people who are quite old and probably can't grasp new and emerging technologies well.
Yeah.
And on top of that, are really bad at regulating things that have been around for a really long time.
Historically true.
And so I guess I'm almost fearful of regulation, that either as a country we'll lose our edge in computing and AI development because of it, or they'll just create such an uneven playing field with the already existing AI developers.
Yeah, right. That's worse than it is. I mean, look, here, I'll tell you one thing that's kind of funny. I'm a Gen Xer. We're completely going to get skipped. We've always been kind of modestly technically facile. Many of us grew up programming and working with computers, whatever, but we weren't digital natives. My kids, digital natives, totally, right? Millennials, digital natives, totally. So we're getting skipped, basically, the almost octogenarians, people my parents' age now, the boomers, are completely own everything. I think very suddenly it's going to turn over to millennials and Gen Zers. I think very quickly. It's just, we're just going to skip my cohort, which is fine. We had a really small N. We were at the trough of the boom. I think the right answer is saying, look, A, I don't trust people in office to generate regulation that actually makes sense, because B, they historically haven't done it. And I don't just mean these people, I just mean historically they've fucked it up left and right. Fine. I think actually it's useful to sit down and say, what would this look like ideally? Because on one hand, it's I agree with you, oh my God, regulation, let's not do this at all. Just try and stop it. It's just not going to work. On the other hand, saying, how are we going to do this in a way that doesn't just impoverish 90% of the population, tomorrow? I'll share with you something, and this just shows you how Puneet's gone, but he would laugh at me, why I'm such a poor investor. I thought autonomous trucks, I don't mean Tesla's driving around, I mean highway trucks, were going to disintermediate something on the order of 38% of rural jobs in the US overnight. So that's an expensive job. It costs a lot of money to have truckers do this. They're relatively terrible at it. They all take amphetamines and run people over or whatever. Having robots do that just seemed to make sense to me, and plus it would be way cheaper. Problem, 38% of rural income was coming from long-haul truckers. 3-8. That's not a joke. You'd think, oh, what's the number one source of rural income in America? Farming, right? Maybe coal mining? Nope, long-haul truckers. A third. So I had this fear, I said, kind of when self-driving cars were really rolling, and they had a couple of these self-driving truck companies, and I'm like, holy crap, 38% of the people are going to lose their jobs overnight, and it's already a delicate part of the country. This is before the whole sort of recent brouhaha. I'm like, we're doomed. Well, luckily, it just turned out not to work yet. But it just turned out not to work. It was slow. But this is an example for you in saying, okay, let's get ahead of this. What is the proper way to regulate this? Not to say you can't make automated trucking because it would put everybody out of a job. Rather to say, what does that transition look like? And then how do we manage it? Because I think there's going to be so much of this. I hate to say it, I think it's like a conversation with my kids all the time. I'm the only real answer that I see is political activism. The thing I see is my generation, too small, we couldn't do anything. We couldn't even get elected. There are just too few of us. You guys can do it. But walk into it saying, here are the risks that matter. And I actually think AI and the disruption that it's bringing with it is going to be one of these once in a millennium, once in 500 years scale change. This is no joke. This is agriculture. This is steam engine. This is iron. Getting ahead of it, this is what I think is so beautiful. It's so many young people are in technology and really do understand this. They grew up with it, much more so than even my cohort. The downside is let's count the number of Gen Z and millennial representatives, just like this big. Luckily, they're all going to die, so it'll turn over pretty fast. And that's my own cohort. I'm almost too old for this shit. I'm like almost 60 years old, right? So I don't know. But I think you're thinking about the problem right. And I think the only real answer is say, I think you guys will have a good sense. Young people have a good sense of what's reasonable and what isn't. And my suggestion is don't hesitate to regulate it.
The one concern, though, is driving things offshore. I mean, how exactly do you regulate something when somebody could just pick up and move somewhere else? You have to have a combination of either carrots that are so enticing that they make people take the sticks, or some sort of global framework that has some anti-cheating mechanism that's effective in order to ensure that it works.
I think it is. I mean, I think whatever framework has got to be much more than like a city, a state, a country.
One word, China.
Yeah, sure, of course.
That they're going all in on it. If we put regulation in that's not smart without the right carrots, it's going to go badly.
Look at OpenAI as an example of like a right way to do this. I hate to say this, right? But these guys are like, look, this is basically a public benefit organization. They're not even trying to monetize it, and they don't even pretend. You read that document, they're like, I don't know, we may not have money in the future, who cares? They're all the way pedal to the metal. There are a couple other technologies that are like that. Nanotechnology, particularly sort of general assembler stuff that's going on. There's a bunch of things that are sort of worth pushing ahead on. The problem is we don't really know what the universe looks like, but the real problem is what you observed. China's doing it. They're going to get there.
Think World War II, think history. The Nazis, evil, came to power, drove out all the nuclear scientists. Where did they come? What happened after that?
Yeah.
We won.
Yeah. All the smart guys came here.
Take away the aspects of good and evil for a moment and just think what happens when you have a brain flight like that.
But here's kind of almost exactly what I mean. I love that example, right? My opinion, and this sounds terrible, but I went to Oberlin in my undergraduate, so I'm just exposing my background. Like, the best way to make that happen is make this an amazing place to live. The best way to make this an amazing place to live is not have it be shitty for 90% of the people who live here.
That's the carrot.
That's it.
Have the carrots, you're gonna have any.
Have all those people come here and go, wow, it's a great place to live. I love it, and I can bring my expertise and do amazing stuff. That's how you win.
So, you keep reading that there is plethora of data sitting somewhere, and like, so cat pictures and dog pictures, of course, internet, there's plenty of it, but like what you're saying on the FTA applications, what data is there and all that. Where is the source of these data? You just keep reading this plethora of data, but I don't understand where is this sitting.
So let's look at three different kinds of data, right?
Yeah.
Data one, there's actually a remarkable amount of public data around genomics, for example, around ClinVar, the clinical effect of genetic variation, for example. There's a surprising amount of that kind of data available today, bulk. If you look at clinicaltrials.gov, it's a required entry for every clinical trial run in the US, but it's not structured very well, at all. It's just you have to answer certain questions in text and post them. People, I think, didn't object to doing that because they're like, what's anybody going to do with this? It's just a big, long, rather confusingly written document. Well, all of a sudden, I mean like last year, you can read those things, turn them into structured documents and find things out, and people are doing that fast. They're like, oh, now I know every clinical trial that's going on in a structured way, and I can start asking questions. Thank you, large language models and machine learning. So there's a lot of latent data out there, and people are doing things with it today. AlphaFold is a good example. Like, hey, for decades, since I was in grad school, you were required to post any three-dimensional structure that you wrote up in a journal, in a numeric form. It was just required. Same thing with gene sequence. This is why GenBank existed. You had to post your sequence, or you couldn't write your journal article. So AlphaFold, an artificial intelligence technique, took all of that posted data and built a thing to predict protein folds, and did it actually pretty well. So there are places where there's a concentration of pretty voluminous data. But for the FDA application thing, right, we did this project, right? We didn't go outside. We went to a pharmaceutical company and we said, hey, you guys have a decade worth of electronic submission to the FDA, and all of the structured data that you use to write that submission, just build a machine learning model that maps the structured data to the unstructured text submission and then have a small group of editors make sure it's factually correct and submit it to the FDA. That represented an 80% decrease in labor to do that submission. But that wasn't data that was out in the world. That was just data that they had. So, like, I think it's a little of both. But lots of those FDA documents are public documents. You can go find them. But they're written in such a way that until very recently, there was just nothing you could do with it. I think people have still kind of not quite caught up to like, whoa, wait a minute. These language models can tear those things apart and turn them into structured data. All right. Well, thank you very much. Thank you for all staying to the last bitter end.